All right, so let's finish off ionic compounds by talking about type 2 ionic compounds. All the rules and the naming are more or less the same for this, especially in terms of writing the formulas. The big thing that's new is just how to address the idea that there's multiple possible charges available. So we're going to quickly go through that, why it makes a difference, and then again at the end there'll be some practice examples for you to pause, try, and then check your solutions too. So real quick, just to review what the term was for type 2. A type 2 cation is a metal atom, metal ion, that has more than one possible stable oxidation state. In the previous video, we talked about the manganese ion that can have 4 different stable states. Copper, as another example, can have 2 different stable oxidation states. Now, these oxidation states, we can see the different type 2s here on the periodic table of ion sheet. Again, I color-coded them black and red so that you can see where they are. If yours printed out only in black and white, you may want to use a highlighter or something to kind of indicate which ones are supposed to be type 2s and which ones are the type 1s, so that it helps you when you try to go write the names and formulas for these things. Now, the different charges on these atoms play a role. They're very important as the properties of these things change completely as they gain and lose electrons. For example, sodium metal, we saw in the reactivity of metals lab, when you put it into water, it can potentially light a fire. Right? Potassium had the little explosion and burst into flames. However, sodium chloride, right, is an ionic compound, and it's what you put on French fries. It's your table salt. If it still behaved the same as regular sodium, it would be bursting into flames in your insides every time you swallowed your food. These charges play a role. They're very important. It changes the bonding, changes the compound, changes the way it interacts. And so as a result, we need to make sure we have a way of differentiating the formulas, differentiating their names. In the picture here, we see, for example, copper metal on the left, whereas in the middle, we have copper ions bound with the sulfate anion. But these copper ions should be copper +1. This is not showing up very well in the video, but this should be a +1 charge here. It's very faint on my screen. And then we have the sulfate, a -2 anion. So based on charge balancing, those two should come together to make this formula here, copper 2, and then sulfate with just one of those. On the right side, you have copper that has an oxidation state of 2+. We see that the color of the compound changes. If you're able to zoom in on the pictures, you see that the grains and the particles themselves change as well. And as a result of the charge balancing, the formula itself also changes, right, the ratio of the ions. If you were just to say, go over to the counter and grab copper sulfate to do a reaction, that would not clearly indicate which of those 2 ionic compounds that you need. So we need to have a way of differentiating the 2, telling them apart, making sure that we're getting the correct one at the correct time. The way we do that is by incorporating Roman numerals into the name of the compound. This is not something that we do for type 1s because there is only one possible oxidation state, so using a Roman numeral to show its charge is just redundant and it's not done. In this case, we have copper on the left, copper metal with no charge. It's not a compound, so we wouldn't need any Roman numerals at all. However, for the copper in the middle, it has an oxidation state of 1, so we would use the Roman numeral of 1. And it looks like this picture that I pulled from Google is all backwards over here. It should be 1, 2, 3. In naming these compounds, what you're going to do is name the cation, the metal, as we had before, where it doesn't change its format. However, after the name of that metal ion, you're going to put the Roman numeral inside of parentheses that represents the charge of that metal. Not how many of the metals there are, just the charge of that metal. So for example, in the middle here, this is copper with a charge of 1. This here is copper 2. Beyond that, everything else is exactly the same. The anion still changes its ending to IDE. If it's a polyatomic anion, we look it up on the back of the periodic table of ion sheet. So again, in total, to put everything together, for these 3 compounds, on the left we have copper metal. In the middle, copper with a +1 charge would join with sulfate to form Cu2SO4, which is called copper 1 sulfate because the charge of the copper is 1. Again, the Roman numeral here does not represent how many coppers there are because we see that there are in fact 2 copper ions. This represents the charge of the copper. And then the one compound on the right with the copper 2 plus ion would form the formula CuSO4, and we would call it copper 2 sulfate. Going in reverse to figure out the names of these things, we're going to need to determine what is the charge of the cation, because we know, for example, in these first two here, iron can have multiple oxidation states. It's also a type 2 metal. So we need to know, is this iron with a 2 plus charge or is this iron with a 3 plus charge? And we do that by looking at the anion and remembering that these compounds need to be electrically neutral. I'm going to split these compounds into the anion and the cation for all of them. We do that by separating the metal from the rest of them. Here we know that we have one Fe, we have one O. In the second example, we have one Fe, and we have three Cls. In Cr2O3, we have two Crs, three Os. And in TiO2, we have Ti and two Os. Now, the charge of the anions never changes. Anions are only ever a single oxidation state. So we can use those to help us figure out what the metal ion charge has to be. I'm going through and I'm putting down the oxidation states for the oxygens and the chlorines based on the periodic table of ion sheet. And from that, we can see that the total charge that's negative on this first compound, FeO, is -2, which means that this total positive charge must be 2 plus. Now there's only one iron atom, so that one ion must have a charge of 2 plus as well, which means that the name for this one would have to be iron 2 oxide. For problem 2, we have a total of -3. We need to have a +3. There's only one iron ion for that. So this second example must be iron 3 chloride. In the third example, we have a total of -6, which means we need a total of +6. There's two chromium ions, which means each one must be a +3 to add up to a total of +6. So this one would be chromium 3 to represent the 3 positive charge, oxide. And then lastly, we have a total of we have a total of -4 from the oxides in TiO2. There's only one titanium ion. We need a total of +4, so that one ion must be 4 positive, which means the name of this is going to be titanium 4, that's IV, oxide. The next sheet is just all example problems. So we're going to pause here again, give them a shot. Let me know how many you get right before resuming and checking out the answers to them. All right, first we have 3 cobalts. We have 2 phosphates. We know that phosphate has a charge of -3, so this gives us a total of -6. We need a total of +6, so each of these cobalts must be 2 plus. Name for this compound would be cobalt 2 phosphate. Next we have ruthenium. We have one of those. We have 3 chlorines. We know that chlorine is -1. Gives us a total of -3. So ruthenium must be +3. Gives us our name ruthenium 3 chloride. Next we have technetium and oxygen. We know oxygen has a 2- charge, so the single technetium ion must be 4 positive. Makes technetium 4 oxide. Next we have gold. There's 2 gold ions. There's 3 oxygen ions. Gold, the oxygens are -2, gives us a total of -6. So each of the golds must be +3 to get a +6. So this is gold 3 oxide. Number 5, we have platinum. We have sulfur. There's 2 sulfurs. Each one has a charge of -2 for a total of -4. Platinum must be +4. So the name of this is platinum 4 sulfide. Then last one, please be very careful. There is always somebody who makes this TISE. This is not TI, this is TL, thallium. There are 2 of those. One of these SEs. We know that selenium always has a charge of -2. So each of these TLs must have a +1 charge. So this is thallium 1 selenide. All right. For the practice sheet, it's going to be online. You'll see that there's a mixture of type 1s and type 2s, binaries and polyatomics. Put everything together, see how you do.